Welcome to the second lecture in Unit 3 entitled Back to the Middle and Around Again. You see a picture of Neil deGrasse Tyson, who's a famous current scientist. He says, "Our galaxy, the Milky Way, is one of 50 or 100 billion other galaxies in the universe. And with every step, every window that modern astrophysics has opened to our mind, the person who wants to feel like they're the center of everything ends up shrinking." Neil deGrasse Tyson. So, the learning goals for this particular presentation are that students be able to relate the structure of the nucleus to the periodic table. We've already covered what's in the nucleus. That you should be able to determine the number of protons and neutrons in an element, and that you should be able to classify certain types of nuclear reactions. So first, what we already know. We already know that the nucleus contains both protons and neutrons in the nucleus. We know that the protons are positively charged, and we know that the neutrons have a charge of 0. And we also know that they have roughly the same mass of 1 atomic mass unit. All that information was covered in Unit 2. Now, what we learned in the lab is that the atomic number on the periodic table is the same as the number of protons. And we learned that the atomic mass is the same as the number of the protons plus the neutrons. So the nucleus. The nucleus contains 99.9% of all the mass an atom has. It's very similar, and a lot of times it's compared to the sun. It's the center of mass, it's kind of what everything moves around. But the nucleus is even more massive than our sun when you compare them to the rest of the atom. So this right here is 99.9% of all the mass of the atom. It contains all the positive charge. So the nucleus can be thought of as a single large positive charge. And the nucleus is what determines the identity of the element. That's what makes this lithium as opposed to carbon or nitrogen, is what the nucleus says. Now, the average atomic mass is this bottom number on the periodic table, and what it represents is the sum of the protons and neutrons in the nucleus. Now, the average atomic mass is just that, it's an average. So instead of it being a nice even number, it tends to be things like 47.867. What that means is that's an average of all the naturally occurring isotopes. For titanium, that can mean that there's a titanium 48 and a titanium 47. And you may be thinking to yourself, well, if there's a 47 and a 48, shouldn't the average mass be 47.5? And the answer to that is no, because there's not an equal split between the isotopes. What this would show me is that there's more titanium 48 and less titanium 47, because it's closer to 48 than it is to 47. So what we have is an average atomic mass that's weighted. It's just like you have in a class where tests may be worth more than daily work. So your grade, your average, ends up being more reflective of your test than your daily work. Now, the atomic mass in the periodic table. The atomic mass generally increases as you move from left to right. So as you go this way, it usually goes up. Now, there are certain circumstances where it does not, and you can see one right in here if you're looking for it. The average atomic mass always increases as you move from top to bottom. So as you move down the periodic table, the average atomic mass does always increase, and you can always find the average atomic mass as being the number below the chemical symbol whenever you look at the periodic table. So early periodic tables were organized by mass. That's what we talked about when we talked about Mendeleev. Mendeleev organized his by atomic mass, and he found some similar properties. Whenever he organized them, you can see vertically that there were some similar properties. But the problem is whenever he did this, there were some inconsistencies. There were inconsistencies because you had some things that were more massive, you had some things that were less massive, and they didn't line up quite as well as they should have. So because of these gaps in the pattern, and you see this specifically with the fourth row, they don't follow the same pattern. So as you see, it increases 51, 54, 55, 56, and then it goes down. So between cobalt and nickel, you actually see as you move from left to right, the atomic mass doesn't increase. So because of that, the pattern doesn't always work. So instead of organizing periodic tables by mass, we decided to organize it by atomic number. And the atomic number is defined as the number of protons that an atom has in the nucleus. The atomic number is identical for all elements. So every single helium atom will have 2 protons. Every single one. Every single time. Now, you can have helium atoms that don't have 2 neutrons. You can take one of those neutrons away. But every single helium atom will have 2 protons. So the atomic number in the periodic table, sometimes the atomic number is referred to as Z. That's the variable that it's usually assigned. It does increase as you move from left to right, and there are no inconsistencies. And it does increase as you move down the periodic table, and there are no inconsistencies. That's why atomic number is used instead of atomic mass. The average or the atomic number is not an average because every single element of titanium will have 22. And so what you see right here is it's always written above the chemical symbol right there on a periodic table. There is a consistent pattern as you move from left to right. You go 19, 20, 21, 22, and so on all the way across to 36. So elements are organized by atomic number, not by atomic mass. Now we did talk about what this is. This is something called nuclear symbol notation that we covered in Unit 2. And so that right here is where we have the atomic mass on the top left and we have atomic number on the bottom left. Now that can be somewhat confusing because it's the reverse of what you find on the periodic table. But it is something that you need to be able to recognize. Something is an atomic mass, or excuse me, something is on the periodic table, or something is in nuclear symbol notation. So we want to match the definitions to the terms. It says depends on the number of electrons. Neither the atomic mass nor the atomic number actually depend on the number of electrons, so we're going to go ahead and cross that out. So next it says depends on the number of neutrons. We know that neutrons do have mass, but we also know that atomic number does not. So we do know that atomic number does depend on the number of protons. Okay, but we also know that atomic mass depends on the number of protons as well. So there's actually two things that atomic mass depends on, and only one thing that atomic number depends on. It says use the periodic table to determine the number of protons and neutrons in iodine. So we look at the periodic table when we find iodine, and when we look at it, we see that it has an atomic number of 53 and an atomic mass of 127. So it looks something like this on the periodic table. What that tells us is we know that iodine has 53 protons. Now remember, 127 represents the protons plus the neutrons. So if we take 127 and we subtract the 53 that we know are protons, we can actually figure out that we have 74 neutrons. So whenever we look at this one, it says identify the chemical symbol, row, and column of an unknown element based on the nuclear symbol notation below. So if you were to look at this, the first thing we do is we say, okay, there are 42 protons. The fact that there are 42 protons lets me know that it's going to be molybdenum, which is MO. Because of that, I can actually write it as 4296. Now, if I want to look and see what column it's in, I would look on the periodic table and I would give it a number. Now, it doesn't actually matter what molybdenum is in because it's in the 3 through 12 region, which is going to classify it as something called a transition metal. So even though we don't necessarily need to specify exactly what column it is, we know it's in the 3 through 12, so it's a transition metal. And we can also identify it as being in the 5th period because it's in the 5th row down. So now when we look at this, we can say, okay, speculate, guess based on evidence, why the periodic table wraps around after 18 columns. So once I get here, how come lithium isn't over here, or beryllium's not over here, or something along those lines? And the best answer that we have at this point is we can say because then the properties won't match up. You won't have similar properties. So if you put lithium over here after helium, it doesn't match up with what its properties are very similar to. So the short answer is this is the easiest way to match the properties of elements in vertical columns. We'll learn about a little bit later that it also tells us where the valence electrons are. So everything in the first column has one valence electron. Everything in the second column has two valence electrons. And so on and so on and so on. Changing the nucleus. You can change the nucleus, but if you change the nucleus, it is no longer a chemical reaction. We're not talking about chemistry at the point where you change the nuclear reaction. Instead, we're talking about a nuclear reaction. Now, changing the nucleus actually requires an enormous amount of energy. Because of that, it is much less likely to occur when compared to a chemical reaction. There are a couple of different types of nuclear reactions that we need to talk about, and the first one is a fusion reaction. And a fusion reaction is basically you start with two smaller nuclei. So I start with something called deuterium, and tritium, which are both two isotopes of hydrogen. And when you slam those together at really high temperatures, really high speeds, you can actually create a helium from two hydrogens. Now, a fusion reaction is much more energetic than a fission reaction, and it releases so much energy that at this point we have no use for fusion other than nuclear bombs. If you were able to generate a sustaining fusion reactor, you would essentially solve all of our energy needs for the entire world. The next thing you have is fission. Fission is the exact opposite of fusion. Where fusion was taking two smaller nuclei and making a larger one, fission is taking a large nuclei, like uranium 235, and splitting it into two smaller ones, such as krypton and barium. Now, fission is still very energetic, but it is less energetic than fusion. Because it is less energetic than fusion, we can actually contain fission reactions. Whenever you can make a nuclear bomb out of fission, but you can also capture it in a nuclear reactor, and you can actually use it to generate different types of radiation. What you see is a nuclear reactor right here. In the nuclear reactor, you have a nuclear reaction that occurs. Whenever you have a nuclear reaction occur, it produces a great amount of heat. The great amount of heat is actually used to heat water, which is then used to turn a turbine and make electricity. Now you have things called control rods that are here, that when you insert the control rods in, it will actually capture these neutrons to slow down a nuclear reaction so it doesn't run away and melt down. The next and last one that we have is something called alpha decay. Alpha decay is a specific type of fission reaction. So it's where you start with a very large molecule, and then what you do is you emit what's called an alpha particle. Now, an alpha particle is just a fancy name for a helium nucleus. So a helium nucleus is something with two protons and four neutrons, or excuse me, an atomic mass of four, two neutrons, two protons. So what happens is you have a larger molecule that splits off a small particle, and then you have two new particles, the alpha particle, and then you have this other uranium molecule. Now, alpha decay is actually used in smoke detectors to detect a fire. So it can actually has a little sensor when something gets in the way. The alpha particles are scattered whenever there's smoke, and it'll actually set off the alarm that way. So it says write the nuclear symbol notation and use for alpha particles. Now, alpha particles are alpha, 2, 4. And what they are, there's a naturally occurring process in which large molecules can go to slightly smaller molecules plus an alpha particle. So it helps stabilize elements because you have a large unstable element that actually goes into a smaller stable element. Next, it says, what advantages would switching to fusion nuclear reactors have if it were possible? You would have clean, cheap, abundant energy. And the reason why is you can take any hydrogen, and hydrogen is present in water, it's present in hydrocarbons, it's present in just about anything. You can take two hydrogens and slam them together, and whenever you slam them together, your only byproduct would be helium. You wouldn't have to worry about things like plutonium and uranium and things like that. You would just make helium, and that helium would float into the top of the atmosphere. It's not a greenhouse gas, so you would produce a lot of energy with a little amount of effort. It would be abundant, it would be cheap, and it would be clean. So describe the nuclear reaction described below. So what we see is we see two helium molecules. They do slam together and they actually produce a larger particle. So because of that, this is a fusion reaction. Now this is actually what happens whenever you have a red giant star. So once a star finishes burning all of its hydrogen, it actually expands and it starts to burning its helium. When it burns its helium, it can produce beryllium just like shown. So it says fill in the missing product of the nuclear reaction. So one of the things that you realize is everything has to balance in a nuclear equation, just like it will in a chemical equation later this year. So I have 236 on the top on the left side, which means on the right side I have to have 236 as well. But the problem is that I have 141 and then I have 3 ones. So because of that, I have 144 right here, which means I'm missing some from the 236 that I need. So in order to figure out what's missing, I would have to say 236 minus 144. Whenever you subtract those two, you end up getting 92. So I know that this missing particle has to have a mass of 92. So now I need to figure out the protons. I have 92 protons and 0 protons, so that's 92 on the left. I have 56 and 0, so that's going to be 56 on the right. There's a discrepancy there, so what I do is I need to be able to figure out the missing. So I say 92 minus 56, and whenever I do that, I end up getting 32. So now you would have 92 and 32. At this point, you would look up your periodic table, and you would find the element that matches 32. And that would go right here, and that would be your missing product.